Welcome to my third and final video about Karl Popper's The Logic of Scientific Discovery. So this is what we found so far. So far we found that science is trying to find universal laws. It can't prove them true, so it tries to prove them wrong. That the job of science is to try its best to prove ideas wrong and not make excuses. Do not protect ideas from being falsified so that we can take the bad ideas and throw them away. The ideas which are wrong, we can prove wrong. Now, there are really two types of scientific laws. One kind is a deterministic law, and a deterministic law is based on regularities which are certain. All A equals B, that is a deterministic law. If you know one side of the equation, you by definition know the other. Some scientific laws work like this, like the laws of physics, F equals ma. So that's the kind of laws we've talked about so far. All A equals B, all swans are black, but it's also the case that a lot of science isn't based on those kind of laws, it's based on the other kind of laws which are statistical and probabilistic. For example, a lot of my work in psychology is based on different kinds of correlation. If people are higher in A, they tend to be higher in B. So if I say there's a correlation between A and B, what it means is that people who are higher in A tend to be higher in B. There's a trend line, but the individual data points are off the trend line. Now, if it was a deterministic law, all I could do is say, oh, the number's off the trend line, therefore the theory is wrong. But if I'm dealing with a probabilistic, statistical law, I can't really do that. So what I'm going to do is I'm going to talk about the logic of how Popper's theory applies to probability. Throughout this video, I'm going to give the example of a law, a statistical law about these swans. So let's say that 50% of the swans are black and 50% of the swans are white. That's the rule. Well, can we falsify it? If I make the claim all swans are white, I can falsify it with one black swan. But now we're expecting there to be some black swans and we're expecting a proportion between them. So how are we going to apply Popper's falsifiability to a statistical rule like this? In order to discuss this, I first need to define probability. Now there are two different ways to think about probability. One way to think about probability, the subjective view of probability, is that probability is a feeling. So how do you feel about this? Well, I feel 50-50, I'm not sure about it. Well, that's the subjective view of probability, that a probability refers to a subjective feeling of someone's confidence. Confidence in a particular claim, for example. Now, Popper rejects this out of hand. He says no. Science is not in the business of saying how confident you feel about something. It's possible that you feel confident about something, but you're completely wrong. Science is instead about trying to find things that are true of the real world. And so he instead uses the objective definition of probability. He uses in this case, the frequentist definition of probability. This is a position, a definition of probability, which says that probability tells you about things in the real world. The frequentist definition of probability is that probability is a relative frequency within a reference class. I'll give you an example of that. If I say that it rains 20% of the time, what I'm really saying is that I have measured a whole bunch of times where it could rain, say a whole bunch of days, and on 20% of those days it rained. So probability is a relative frequency, the proportion of times that something happens within a given class of events. That's how he defines probability. Now, probability is often taught as if it comes from experience. So, from what happens if you roll a bunch of dice or flip a bunch of coins. Although that's a good way to teach probability, and I've taught it myself that way, if probability were based on experience like that, it would be fallible to the problem of induction. The good news is that probability is actually based on mathematical laws which are certain. So the rules of probability, the theorems of probability, are actually based on mathematical rules, mathematical logic, which comes from deduction, we can actually trust the laws of probability. So one law of probability is Bernoulli's theorem. That's called the law of large numbers, which is basically if an event has a real probability, say the real probability of getting heads on a coin flip is 50%, then the more times you flip a coin, the closer you'll actually get to that 50%. And what Popper does, and he takes a surprising amount of the book to do this, is he goes step by step explaining how you would create a random sequence of numbers in order to prove this theory of probability. So he goes into quite a lot of detail about this, but the point is that the theories of probability, they're logical and we can trust those so far. Now here is the difficulty. The difficulty that is that a statement about probability is by definition unfalsifiable. It can't be proven wrong. If I say of a set of swans, 50% will be black and 50% will be white, well, what I can do is I can measure a bunch of these swans, and even if I look at them and I say, oh look, it's 100% black swans, then I still can't disprove that probability statement that it's 50-50, because maybe in the other lake it's 100% white swans. Because what a probability statement is doing, when I'm saying that something is true of all white swans, the reference class is all of them, and I can't measure all of them. I can't say that 50% of the swans are black unless I've measured every single swan that could ever exist in all possible places, and then actually measured that half of them are black swans. So a probability statement, in theory, is unfalsifiable. Now, this seems to be a real blow to a lot of science which relies upon probability. However, what Popper does here is he separates what we've just discussed, mathematical probability, from what he calls practical probability. So mathematical probability is a probability statement based on logic, whereas physical probability is a probability statement about things that you're actually measuring in the real world. So physical probability, the way Popper describes it, physical probability is the probability of things as they actually happen in the real world. We've got all these pieces of air in the room, different particles of air, and they're all kind of moving in a random way. It's possible for all the pieces of air in the room to randomly wander off into the corner, and I would need to hold my breath. So that is mathematically possible, but it's also unbelievably improbable, and so it's so negligible that we don't need to worry about it. And so what Popper says is that when you're making empirical observations, what you're doing is you're using physical probability, so the probability of what actually happens. And then you can falsify probability. So let's go back to the example of the swans, 50% white, 50% black. Now, different samples are going to tell me different things. So maybe I get some samples where it's 50 of one, 50 of the other. Maybe it's some samples where it's 49 and 51. Maybe it's some samples where it's 60-40. However, it is unbelievably unlikely for me to get a sample where it is 99 black swans and 1 white swan. So what I can do is I can begin with the claim that it's 50-50. And then what I can do is I can say, given this claim, what is the probability of seeing the result? Given this claim, what is the probability of seeing the 99-1? And if that probability is unbelievably low, that it's negligible, then I can falsify my claim. And this is very similar to what we're doing in statistics, in null hypothesis significance testing. What you do is you begin with a hypothesis. For example, the relationship between A and B is 0. And then you say, given the hypothesis, is the probability of what we've seen negligibly small that we can reject the hypothesis? One thing that Popper says is that one falsifying result isn't enough to reject a theory. And this includes a probability theory, a probabilistic theory. Because if you measure enough samples, at some point you're going to get the 99 to 1. However, what you need to falsify it is you need to replicate what you found. You need to 2 or more experiments to repeat the same result. Because remember, what we've got here is assuming that the null hypothesis is true, that it's 50-50, there's going to be some variation, and the variation will be random. And if one time I see 99-1, then I can't manipulate my experiment in such a way that the next time I'll get the 99 to 1. And so if I see 99 by 1 a bunch of times, very clear evidence, very low, unbelievably low physical probability, and therefore I can reject the claim. And that means that Popper's rules about falsifiability apply both to deterministic rules and to statistical probabilistic rules as well. And so we can actually use it in the statistics of science. Now, the next question you might ask is, okay, so Popper tells us that we can't prove things true. We can't prove things true. Well, is it possible that we could be confident of our theory, right? So Popper said, I can't prove my theory true. Well, maybe I could prove it with 99% confidence. Can I use probability that way? So what Popper is talking about now is the probability of a hypothesis. The probability not of an event, but the probability that a theory is true. So is it possible that you could have a probability that a theory is true? And Popper's answer to that is no. You cannot have a probability that a theory is true. Because remember how probability is defined. Probability is defined as a relative frequency within a reference class. So when you say there's a probability of a hypothesis, it has to be X% out of something, but it doesn't make sense to have any out of something, given that that strictly universal law implies an infinite number of things. So it's impossible to actually create a probability of a hypothesis in that way, because the reference class would be infinite. What would it even be? Would it be all possible worlds in which the theory may or may not be true? And so it's actually impossible to come up with the reference class from which to calculate the probability. And as well as that, let's imagine that we could work out the probability of a hypothesis. And let's imagine we could work out the probability of a hypothesis and we wanted a high probability of a hypothesis. Well, how would we do that? Well, the way we would do that would not be good falsifiable science. Because what we're doing with a scientific claim is we're making a claim that's precise and specific and strict, and it rules things out about the world. And what that means is that the more things it rules out, the more falsifiable a claim, the more things it rules out, the lower the probability of the hypothesis were it to exist. So if you really wanted to have a high probability of a hypothesis, all you would do is make really vague claims. So I could make the claim, all swans are black or white. Or I could make the claim, tomorrow it will or will not rain. That has a probability of 1, but it doesn't have empirical value. So what Popper is saying is, 1, you can't actually get a probability of a hypothesis, and 2, even if you could, it wouldn't be a good idea. So what does that leave us with? What that leaves us with a state in which science cannot prove theories true, and also it can't even give you confidence about theories. So what science can do in summary is it can tell you 2 things. It can tell you either this theory is wrong, or this theory has not yet been proven wrong. Those are the only 2 options. Well, what good is that? What is the value of having a scientific theory? Now, Popper introduces the concept of corroborability, the degree to which a theory has been corroborated. And what that means is how much a theory has survived what he calls severe tests, genuine attempts to prove the theory wrong. Because remember, we can't prove a theory true, but what we can do is we can try our best to prove it wrong. I'm going to end by giving an example of corroborability. Now, a long time ago, there was a ship called the Titanic. And it was said of the ship that it was unsinkable. And the ship wasn't unsinkable. it was hit by an iceberg. Well, let's imagine that there really was a ship that was unsinkable. You can falsify that hypothesis, you can see if it sinks. However, it's not verifiable. So if a ship was unsinkable, then what I could do is I could try different ways, different tests to try to sink it, and if it doesn't sink, I still don't know it's unsinkable. Maybe another test could sink it later on. And so the statement, the ship is unsinkable, is unverifiable, a bit like these natural laws. Corroborability is the degree to which something has stood up to genuine attempts to prove it wrong. So it's a bit like this. If I had a ship and I said, go on this ship across the ocean, it's not been tested by anything, well, then there's no corroboration for the statement, this ship is unsinkable. However, if I say, this ship is unsinkable, remember, I still can't verify it, but I have tested it by trying to sink it, punching holes in it. I've gone through terrible storms and I've gone through the ice and I've hit it with cannonballs and all sorts. If I've tried my best to sink the ship and I can't, then that gives corroboration to the theory that this ship is unsinkable. And so what that means is that what science is doing, it can't prove claims, but what it is able to do is it is able to generate claims that are able to survive severe testing, and so we can say that is our best model of the world for now.